Today we're going to be talking about matter. And so here are some of the objectives that I want you to be able to accomplish by the end of today. Now, a lot of this is just in the textbook, so I'm going to try to show some examples and build a little bit. But I'm going to go pretty quickly through definitions, okay? So, where do we start? What is matter? Matter is anything that has mass and takes up space. So, what about some examples? Well, water has mass and takes up space. A rock has mass and takes up space. A building has mass and takes up space. What about air? Does air have mass? Well, yeah, actually it does. Does it take up space? Yeah, it does. So, air is also an example of matter. Matter is composed generally of some varying types of building blocks, okay? So the smallest building block that we're going to talk about for now is an atom. Now, keep in mind that atoms are actually composed of even smaller building blocks, but for now we're talking about atom as the smallest unit of an element that maintains the identity of the element, okay? And we know that elements are, or atoms are, made up of protons, neutrons, and electrons, okay? So for example, I could have one proton, no neutrons, and one electron, and I'd have an atom of hydrogen, okay? I could add a couple more, add a couple neutrons, and some more electrons, and I'd have lithium, okay? Now, we're going to use a lot of models when we're talking about things that we can't see. So this is an example of a model. This model uses electrons in orbits. You might also see electrons in clouds, okay? We're going to deal with that more later. But for now, it's important to know that there are protons, neutrons, and electrons in an atom. Okay? Now, the atoms generally make up elements. And an element is a pure substance that cannot be broken down into simpler, stable substances and is made of one type of atom. Now, you might think, hey, these seem a little bit redundant. But, as I'll show you later, there are elements that don't form single atoms, okay? In nature, if you find them in nature, if you find them as a stable thing, they will have more than one atom, okay? We call these, they generally have two, so we call these diatomic elements, all right? And then there are compounds. A compound is a substance that can be broken down into simple, stable substances. Each compound is made from the atoms of two or more elements that are chemically bonded to each other. So, for example, if I have an oxygen and I have two hydrogens that are chemically bonded to that oxygen, I'm going to make something called water. Hey, all right. And we have models as ways of representing this element, or this compound, sorry. One of the ways that you'll see this commonly represented, especially in the book, is with a space-filling model, where each element takes up space, okay? Each atom takes up space, and so that space is represented. So hydrogen is the smallest element, smallest atom, okay? So it's going to be smaller than something like oxygen, which is bigger, okay? I could also represent this as a ball and stick model, where this stick now represents a chemical bond, and the balls represent just atoms, okay? So that's water. Now, these can get significantly more complex, these compounds. So something like sugar, which has C12H22O11, all right? That is significantly more complicated than water. Now, a compound can be broken down into simple stable substances. So here's a kind of cool apparatus. If you take water and you run electricity through it, that electricity is able to break the bonds between the hydrogens and the oxygens. And so you end up creating pure elemental oxygen and pure elemental hydrogen. Now, hydrogen and oxygen are both diatomic molecules. So when you break the water down, you actually create diatomic elements, oxygen, which is two oxygen atoms bonded to each other, and hydrogen, two hydrogen atoms bonded to each other. Okay, so this is an example of a compound, water, being broken down into molecules of oxygen and hydrogen. We're going to come back to our discussion of matter a little bit more, but I want to transition now into some more things. So, intensive properties versus extensive properties. These always give people trouble. Okay? Intensive properties do not depend on the amount of matter. So do not depend on amount of matter. Whereas extensive properties do depend on amount of matter. Now, let's go through some examples. So, an example of an extensive property, something that does depend on the amount of matter. Well, that'd be something like volume. Okay? If you add more matter, if you add more, let's say, water, you're going to have a bigger volume. Okay? You will also have a greater mass. This is an example of an extensive property. Intensive properties do not depend on the amount of matter. So something like density, or something like melting point, or something like ability to conduct electricity. Now, what's cool about intensive properties is that these can be used to identify a compound or to distinguish between different compounds. Okay? Extensive properties aren't so helpful with this because I could have like 1 milliliter of water and I could have 1 milliliter of ethanol. And I couldn't tell the difference between the two using extensive properties. They'd have the same volume. Okay? I could use intensive properties, but not extensive properties. So for example, if I've measured these out very carefully, not using a beaker, remember, but using a graduated cylinder, if I had 100 milliliters of water, let's say that this is water, okay, my volume would be 100 milliliters. Okay, and if I was very careful in my measuring, and then I took the mass, that would be 100 grams. Okay, and over here, now I have 150 milliliters of water. So my volume is 150 milliliters, and my mass is 150 grams. Okay, so these are extensive properties. The volume changed, and the mass changed. Okay, an intensive property, however, wouldn't change. So an example of this would be density. So density is mass divided by volume. So 100 grams over 100 milliliters equals 1 gram per milliliter. And here, the density is 150 grams over 150 milliliters. That is 1 gram per milliliter. So it didn't change, okay? So that's an example of an intensive property. All right, the next thing that kind of trips people up in this unit is physical changes, chemical changes, and physical properties, chemical properties. So a physical property can be observed or measured without changing the identity of a substance, okay? So you could melt water, okay? And you could see the temperature at which it changes state. And that would be an example of a physical property, okay? Because it's still water, right? So a physical change does not involve a change in the identity of the substance. So examples, something like melting, or obviously boiling, okay? So a change in phase will always be a physical change, okay? What about, like, taking a piece of wood and cutting it in half? Well, you still have wood on both of those new pieces. So this would be an example of a physical change. Or tearing a piece of paper in half. Okay, I had one piece of paper, now I have two pieces of paper. Okay, very simple. Chemical changes. A chemical property is the ability of a substance to undergo a change to a different substance. All right, so a chemical change would be converting one substance to another substance. Okay, so this would be if instead of cutting the piece of wood in half, I now took one of those smaller blocks and I burned it. Okay, I no longer have wood. I'd probably have some leftover coal, some leftover carbon, and I would also have a lot of carbon dioxide and water. And we're going to talk more about that later. Okay. How do you identify if a chemical change has happened? Well, there are a couple hallmarks. You might form a gas. So if you do the classic acetic acid and vinegar, okay, so this would be, vinegar and sodium hydrogen carbonate, which is baking soda. So if you take baking soda and vinegar and you mix them, a lot of people do this and they add a little bit of red food coloring and voila, you have a volcano that spews out stuff. One of the things that's cool about this is when you mix these two things, a lot of gas is produced. And that's the hallmark of a chemical change. Okay? You might mix two liquids and form a solid. And that solid is called a precipitate. And we're going to do a lot with that later. So knowing that is good. You might produce a lot of energy. So heat, light, burning, basically, right? Or you might produce a color change. Okay, so when phenolphthalein is added to ammonia, dissolved in water, a color changes from colorless to pink. Okay, that's an example of a chemical change. All right. Phases of matter. So here's a model of some hydrogen atoms, or sorry, not hydrogen atoms. These are water molecules. Okay, and right now I have these in a liquid state, and this is at 328 Kelvin, which is around room temperature. It's a little above room temperature. Okay, and as you can see, the water molecules are free to move around. Okay, they have a definite mass, but they don't have a definite volume. Water will tend to fill the container that it's in if it can. Okay, so this is an example of a liquid. Okay, a solid has a definite shape and a definite volume. So think of like an ice cube. So here's water again, and this is below zero. So this now shows you that these molecules, these water molecules, are in a shape, and they stay in that shape. Now, it's important to realize that these water molecules are still moving a little bit. Even in a solid, they're still moving a little bit. Okay, we'll talk more about that later. And now, if I have a gas, okay, gases have no shape and no volume. They'll tend to fill the containers that they're in. All right, so here are my water molecules, and they're just freely moving around. Okay, they have a lot of energy, but that's what they are. There's another one that there's another phase of matter that we talk about a little bit, mostly in this unit, and that is a plasma. And a plasma is just a high energy state where the electrons are not tightly held by the atoms. And what's kind of cool about that is that the electrons, that makes plasmas really good conductors of electricity. So things like neon signs, okay? There's an electric current that's flowing through the neon gas, which is normally not a very good conductor, okay? And that heats it up, heats the neon up, and creates a plasma. And those electrons are free to move and conduct, okay? All right. Pure substances cannot be separated by physical means. All right. Simple enough, right? Mixtures, on the other hand, can be separated by physical means, meaning it's composed of two or more pure substances. So a pure substance might be something like water, okay? And a mixture might be something like salt water, okay? So salt water can be separated by physical means. If you heat up salt water until you evaporate all of the water, you've broken that mixture, you've separated that mixture into salt and water, okay? A mixture, as mixtures are two or more pure substances, they can be uniform in composition, and we call those homogeneous mixtures, or they can not be uniform in composition, and that would be heterogeneous mixtures, okay? So, for example, I have here a beaker of sugar water, okay? So you can see there are these big sugar molecules that are surrounded by water molecules. But when you look in here, you don't see the sugar molecules. They've been completely dissolved by the water, okay? It has a uniform composition. If I look at a little bubble over here, it's going to look just like this. And if I look a little bubble down here, it's going to look just like this. Okay? Now, here is an example of water and sand, silicon dioxide. Okay? Sand does not dissolve in water. So what's going to happen is you're going to get a little clump at the bottom, and then the top is going to be mostly water. Okay? So this is an example of non-uniform composition, or a heterogeneous mixture. Okay, so the cool thing about this is I can kind of combine everything that we've learned so far into this little table that your book has. And I just like to run through this because it's kind of an interesting, it helps you remember everything kind of graphically. So, matter. Can it be separated? Well, if it can't, it is a pure substance. And if it can, it is a mixture. Okay, so let's go down the pure substance route. Can it be decomposed by ordinary chemical means? See if you can come up with what it is if you can decompose it and what it is if you can't decompose it. Okay? If you can decompose by ordinary chemical means, you get a compound like water, sodium chloride, which is salt, or sucrose, which is sugar. No, you can't decompose it by ordinary chemical means. You get elements like gold, aluminum, oxygen, chlorine. Yay, okay? So let's go back up here. Can it be separated? Yes. If it can be separated, it is a mixture, okay? Does the mixture have uniform composition? Pause. See if you can do the same thing here. Yes, it has uniform composition. No, it doesn't. What are those things called? A mixture that does have uniform composition is a homogeneous mixture. So air, sugar and water, stainless steel. Interesting. A lot of people don't remember that there are these things called alloys. And alloys are mixtures of metals. Okay? They're mixed when they're liquids, and then they solidify. Okay? but they are uniform in composition. If the composition is not uniform, it is a heterogeneous mixture. So think of like granite, wood, blood, anything like that. Okay? So this table, which is figure 2.6 in your textbook, is actually a really good table to know and be able to like figure out whether or not something that I'm describing is a mixture or a pure substance. Maybe I'll even ask you to go a little further into like elements or compounds, those kind of things. Application. Application is important.